Okay, today is July 6, 2014. My name is Jason Ross, and I'm going to be hosting an overview of Kepler's new astronomy. This is part of, please mute yourself if you're connected live. Also, if you have the link to get on live and didn't because you're worried that it would be overcrowded, it isn't yet, so feel free to jump on if you can. So, why is this happening? What are we going to do today? We're looking at Kepler for a couple of reasons. Let's go back and actually look at the initial foundation of the basement process. That was in 2006, and the assignment from Lynn was to animate the creative process pursued by Kepler in his new astronomy to both get an understanding of what science is and also to make a specific point about economic cycles as orbits. The result of that was a couple of web pages, which you can find at science.larouchepack.com, and then you'll find a new one and the original one from 2006-2007, that period. I know that people from different levels are watching this, and people are familiar with the book, some people have never read it before, so I'm trying to aim towards everybody. Which means that there's going to be some things that might seem slightly repetitive to you or things that you don't understand. There's really not any way around that, so sorry about that in advance. And we're just going to go ahead and jump in now. I think what Megan had done on Wednesday in her presentation on Kepler's life and what Kepler was trying to do is gives us a good foundation to move ahead. The one thing I want to refer back to is that in the Mysterium Cosmographicum, Kepler's first published book from 1596, he had tried to answer the question, as Megan described, why are there 6 planets instead of 3 or 10? And why do they have the orbits they do? In other words, one might imagine, you know, any number of planets around the sun. You could imagine that they have any sorts of orbits. Why those ones and not others? Well, Kepler tried to figure that out in the Mysterium Cosmographicum. He came up with this model of the Platonic solids, providing a basis for the different distances between the orbits. And he also pointed at something that he really wanted to figure out that had never been done before, which was to have a planetary model with the sun in the center. You've probably heard that Copernicus already did that. He did, and we're going to be getting into that. What Kepler wanted to do was to re-understand how it is that the planets move to get their exact orbits to then come back and answer the question that was provoking him in the first place of why do they have the orbits that they do? What's the purpose? What's the plan? And you can't do that if you don't know what the orbits are. So in order to understand any of this, let's take a look at some basics of astronomy. What do you see in the night sky? What do you see over one night? What do you see over many nights? And the videos I'm going to be playing are all, for this first part of the book, are on the new astronomy site at science.larouchepack.com. So let me switch over to that. So here you've got a, you know, this is during the night. You know, you see the, let's say you stay awake, and you see the sun moving in the sky. The sun sets. Beautiful night, not a cloud to worry about. You see the planet, you know, you see the stars moving. Very nice. Now, this is called, I'm going to throw out some terminology, which will be important in the in what you're doing in part 1 for the homework. This is the first motion. You go out at night, you watch what happens. That's the first motion of the stars. We're facing south, presuming we're in the northern hemisphere. Our view here, yes.
Probably. You gotta switch it over. You gotta switch it over to the video.
You're not seeing the video?
So we can see it.
Right. Right.
Do you see a video right now?
You have to go to the Jason. You gotta click on Jason's.
Oh yeah, yeah. Look, if you're watching it live, you actually have to click on that other one. It should be fine on YouTube.
Oh, okay.
Okay. All right. So this is called the first motion from night to night. Now, what you can do is, if you do this every night, and you're able to actually piece out what happens. Here's all the constellations. Okay, here we go. Now what we're going to see is from night to night, if we come back out and the stars are in the same position, watch what the moon does. You can see the date in the lower right-hand corner. From night to night, if we go out when the stars are in the same place, the moon is moving, as we see it, to the left, to the east. Remember, we're facing south. So the first motion of all the stars and the sun goes from east to west, as you know, we see the sun do every day, or the stars do at night if we look at them. However, against it, the moon appears to be moving to the left. Does that mean the moon is moving slower than the stars? Every night, it means the moon is moving slower than the stars. However, astronomers figured that something else was happening and that the moon's actually moving to the left. Now, let's take a look at one specific, we're gonna zoom in on one specific star here. And we're going to watch it from night to night. Hopefully the rest, you can see that. You see that reddish star is moving up and to the left. Night to night. The reason the stars are still is just we're looking at them at the same star time every night. Not the same time on your watch, though. Okay. So that was a. So that's a planet. Planet, the Greek word for wanderer, gives us the word planet. So some stars, you know, the moon's pretty obvious. The moon changes phases. It disappears when it's a new moon. It gets bigger and smaller. You know, that's kind of, it's hard to miss that. I bet a lot of people have never actually looked at the sky and noticed that some of the stars move from night to night. It's certainly possible to miss the fact that the planets move, or even notice them, because you can't tell it's a planet unless you see it a couple of nights. I mean, there's some things about how they look, but basically, you know, you actually have to look night to night to night. It's a motion you only see in your mind. Your eyes can't perceive it. Your eyes can't perceive that first motion either. It's so slow. You just notice it over time that, hey, the stars moved. So those are that's one of the planets, Mars. So the basis of astronomy had been to figure out how those things moved. If you're feeling really adventurous, you might even talk about why they moved, what they're made out of, what's going on in the heavens. But for official astronomy up to Kepler, if you figured out where they would be, that was good enough. That was your job. That was the job of an astronomer. It was a part of mathematics. So let me show you another funny thing that these planets do here. Switch over. Okay, rewind that. So the view here is focused on. There we go. The view here is focused on Mars. It's the red dot you see in the center of your screen. We're going to watch it move. So it's moving left against the stars. This is over, you know, months. Goes backwards, and then heads back in its original direction again. I hope you saw that. You'll see it again. Now, obviously, the fact that's the sun passing right by Mars, this is a simulation. You would never actually see this. Even on a dark night, you don't see the blue lines connecting the constellations since they're not there. So here we go. In Taurus, Mars this year is going backwards and then starting forward again. That's called retrograde, meaning it's going backwards. So we got some clues here with these stars. The main unusual thing is this retrograde motion. So now let's go ahead and jump and look at how, let's go through part one of the new astronomy. In part one, Kepler proves that the way that three predecessors of his, Ptolemy, Copernicus, and Tycho Brahe, that the way they explained the motion of the planets, although it seems quite different, is actually equivalent. So let's go through why that is. And let's take a look at their models. So here we go. Oh, switch screens again. Oh. Okay. Great. So, oh yeah, let's start with Ptolemy. So here's a rough idea of Ptolemy's model of Mars. The red dot, the small red dot that you see, is moving around. So first off, you see the Earth's in the middle of everything, and the sun is moving around the Earth, and unfortunately, it's running into the orbit of Mars. It doesn't really do that in Ptolemy's system. This is just an exaggerated animation. And then Mars is going around the Earth. Now, you see that extra second circle on Mars. That's so that, watch it right now, it's about to go backwards. There we go. That second circle that Mars moves on is called an epicycle. Epi meaning, upon or on top of. So you've got, in addition to the small red dot moving around what's called a deferent, you have also an epicycle. So the way that Ptolemy explained the motion of Mars is he said that overall you have that deferent that's moving, you have the motion on the deferent, and then around that point there's also an epicycle which carries Mars and makes it go backwards from time to time. That might seem a little bit silly, certainly does to us, doesn't it? But that's what he said. Then you had Copernicus, who you've no doubt learned put the sun in the middle of everything, said that the Earth moved. He did say that the Earth moved, and that was certainly contentious in some circles. He didn't put the sun at the center, though. The sun's near the middle, but the orbits of the planets for Copernicus don't have anything to do with the sun. If you removed the sun, you wouldn't have any trouble calculating anything with Copernicus, because the center of the, so let's take a look. I hope you can see the pointer here. So this is what's called the line of apsides. It goes from one apse to another apse. It's the place where Mars is farthest and closest to the sun. And through it, you've got this point here, just called an equant, which we're going to look at in a moment. We have the center of Mars's orbit, the middle gray point. And then right here, we don't have the sun for Copernicus. We have the center of the Earth's orbit. So when Copernicus is calculating planetary orbits, they're not based on the sun. None of the orbits of the planets, their lines of apsides, to do with the sun at all. They're all actually based on the middle of the Earth's orbit. You might say, why would Copernicus still make his system centered on the Earth instead of the sun? We're going to get to that too. He didn't have to. Kepler was the first person to actually use the sun. One more person, Kepler's one-time boss, short-term boss, Tycho Brahe, he said that the planet moved around the sun, which then moved around the Earth. Except Mars didn't really move around the sun, which went around the Earth. You'll notice that, again, this Mars orbit for Tycho Brahe is near the sun. For Tycho Brahe, really, Mars moves on a circle that has as its, what do you call that? Thumbtack. It gets pinned to an imaginary point that's centered on the Earth, and it's not the actual sun. So none of these guys are all actually using the Earth. And where the sun appears, it's just something that you see in the sky. It's not used in their planetary theories at all. So this was a peculiar thing to Kepler, because he thought Copernicus was right, that the sun not only sat nearer to the best, seating position to watch the planets, but that the sun made the planets move. So let's take a look at another video from the website here about how the equant works. Let me shift over to that. There we go. Okay. So let's start with what you're seeing here. Oh, let me make sure you can see it. Okay. What you're seeing here is we're watching over time, we're watching Mars do its retrogrades. So as usual, Mars generally moves to the left against the stars. Sometimes it goes backwards, goes to the right, and then continues moving to the left. So this is showing over many years. This opposition occurs about every 2 years. this retrograde occurs about every 2 years. So we're building up a catalog of what happens. And let me speed it up a bit. Okay. What you see on the top of the screen is the retrogrades excluding what's called the latitude, never minding the fact that the planet moves up and down in addition to moving to the left and then sometimes to the right. Uh-oh. Okay, so let's pause it there. So what you see right now is that there's one part of the planet's orbit, if you can see the pointer around here, there's one part of the sky where Mars rarely goes backwards. And when it does go backwards, it does so for only very short distances. You have another portion of the sky towards the left and on the right there, where Mars frequently moves retrograde, and where when it does so, the loops are longer. Let's look at how that got explained. If if the planet moved simply in a circle, if Mars just moved at a constant speed, you'd expect all the retrogrades to be about the same. So the first thing that was done was to say that was to take the orbit of Mars. Remember, this is Ptolemy, so it's going around the Earth, and move it off-center from the Earth. Say Mars moves around a point that's not the Earth, it moves around over there. Now, if we watch Mars with its epicycle, we will get retrogrades that look like this. You can see how it's transforming itself there. So this is putting the retrogrades in the right places. It's more often happening where it's supposed to happen more often, and it's more rarely occurring where it's supposed to happen more rarely. But the sizes of the retrograde loops are they're just backwards. So what Ptolemy did to fix this was he adjusted the orbit a little bit more. And he said that there's 3 points that make up the orbit. There's the Earth, there's that blue spot called an equant, around which the planet moves at a constant speed. And then there's that white spot, which is the center of its orbit, the circle that it actually moves on. Let's watch that motion. I'm also noticing that this video seems not to be working well on YouTube, so I'm going to try and not use the video so much as this goes on, since it's not worth much if you can't see it. It keeps turning off. Okay. Anyway, so Ptolemy's got this thing where he so Ptolemy's got this equant that makes a planet move at different speeds, and then on top of that you have the epicycles, which explain why it goes backwards. Anyway, these three systems I think that I showed all look very different. Kepler's first goal in part 1 of the new astronomy is to show that they're equivalent, which he does, which we can show here by having a look at transforming between them. That, like for example, between Ptolemy and Bra, hopefully you can see this, the actual planets don't change their position at all. It's really just a change of all the paraphernalia that puts them in their places. Okay, watch that again. Okay, so absolutely nothing happens between Ptolemy and Bra. Very straightforward. And then the same thing is also true with Copernicus. When we go from Tycho Brahe to Copernicus, it's just a simple shift of whether the Earth's going around the Sun or if the Sun's going around the Earth. The relative positions of all the planets don't change one bit. It really doesn't matter. You could have them all go around a spot that's in between the Earth and the Sun if you felt like it. Doesn't make any difference. So Kepler shows this general equivalence, and then he's got to make the point that he wants to use the apparent sun. That he wants to use the real sun for what he's looking at. The to use these funny terms, the mean sun, mean means average. So the sun was determined not to move around the Earth. I mean, where the Earth was determined not to move just in a circle around the sun because of the different lengths of the seasons. That's the first clue that there's something non-circular about the Sun-Earth orbit. So based on the different lengths of the seasons, you can estimate where the line of abscides is, in other words, which direction against the stars is the Earth orbit around the sun, and how far away is the center of the Earth's orbit from the sun. So that had been known, for thousands of years at this point. And the mean sun was an imaginary sun that moved at a constant speed around the Earth. If the mean sun was actually the sun, our seasons would all be the same length. The reason it was used was because Ptolemy made his epicycles. I'm realizing some of this is going to be difficult since the video is not working as I would have liked. Since Ptolemy makes his epicycles move directly around the point on the deferent instead of being off-center like the Earth, like the Earth's sun, he has to use this imaginary sun to say when the Earth, Sun, and Mars are in what's called opposition. Let me show a picture of that. Okay. So here you've got the Earth and Mars, and every couple of years, Earth and Mars are in the same direction as seen from the Sun. This is using the Copernican model, of course. So by looking at Mars on these special days, we're able to remove that retrograde motion and look only at the motion of Mars itself. The terms used in astronomy for this, right now what we're looking at is called the first inequality. So the overall length of the Mars year and what part of the sky it generally moves faster at and generally moves slower at, where it generally has short retrogrades and infrequent ones, and where it generally has longer retrogrades and more frequent ones. That's the first inequality. The second inequality is what yanks it backwards every so often and causes the retrogrades and the overall change in speed as it moves. The reason for that is just, of course, that the Earth is moving, and so when we move, it changes how Mars appears to be. But those are the terms that are used. The first inequality is the motion of Mars. The second inequality explains the retrogrades. For Copernicus, the second inequality is the motion of the Earth. And for Ptolemy, the second inequality is the epicycle. So Kepler finishes off part one of the book by showing that if he uses the actual sun instead of the mean sun, the change in the first inequality, the change in where the sun or the mean sun would see Mars, is only 4 minutes. A minute is a 60th of a degree. That's not very much. That's a pretty small difference. And Tycho's assistant Longomontanus claimed to have a model that could describe the first inequality within 2 minutes. So Kepler's first saying, well, this guy, Tycho's assistant seems to have a pretty good model. How can I show that I can compete with that? By showing that the difference would only be at most 4 minutes if Mars was at just the right place. That's the most that the models might differ in that way. But then Kepler looks at the, I'll show you a picture of this one. Kepler looks at where, don't be scared, Kepler looks at where the Earth would see Mars. So here, oh, you got to brush up on your Greek letters here. This thing that looks like a V, this green V, is actually a nu. When the Earth is at nu, you can see these two spots where the Mars might be, at epsilon and at rho, based on using the real sun versus the fake sun. The difference is over 2 degrees. This means that Kepler has shown that when the Earth is watching, there's a huge difference between a model based on the mean sun and one based on the apparent sun. The point of that meaning, we can actually decide which one's right. 2 degrees is a very big difference. and that's one that's decidable in astronomy. Now, I know that so much of this is might be very potentially difficult, that I'm going to stop after every part and take questions instead of going to the end, because I think that would not work very well. So based on what we've gone over so far, people have any questions? General ones are fine, too.
Well, you said that the first hypothesis that the orbits weren't circular was because the seasons' lengths were different. Not that we have seasons, the length of the seasons was different.
Yeah, the first hypothesis that the second that the solar, so let's forget Copernicus. Let's say the Earth's at the center. The first hypothesis that the sun didn't simply go around the Earth was that the seasons are different lengths.
Yeah.
Which means that the sun spends more time on a certain side of the Earth against the stars than on the other side of the Earth against the stars.
Right.
So they say, well, how do we explain that? Well, let's say the sun, let's stick with the circle. The sun moves in a circle. The sun moves at a constant speed. It just doesn't move right around the Earth. It's a little bit off center. And if we move it off center, then we'll get these different season lengths. I'll just draw a little picture of that. Wow, I'm sure this will work great. Okay. Uh-oh. Now the contrast is, you can't see it at all.
It's hard to see.
Yeah, okay. All right. Well, you can draw it out for yourself there. What I basically did is I just drew a circle and divided it evenly into four pieces. I drew a big plus sign in it. And then if you put a point off center, and then look at the angles to those four spots on the circle. In other words, if you were standing on a clock and you weren't at the center, and you looked at where the 12, the 3, the 6, and the 9 were, they'd have the angles between them wouldn't be 90 degrees if you weren't standing on the center. So it's like that for us in the seasons. The seasons occurred in yes. Yeah. The seasons occur when the sun is exactly 90 degrees away in terms of where we see it against, where it appears against the stars to us. Mm-hmm. So that while those are 90 degrees, they're not actually evenly cutting up the whole orbit of the sun. So Hipparchus, Apollonius, well before Ptolemy, people said the sun does not move around the Earth. It's off-center. It's eccentric. It's x-centric. It's out x of the center. It's out of the center. Mm-hmm. So, any other questions about part 1 so far?
Can you reiterate what the first and second inequality is?
Sure. The first inequality, the first inequality is the overall motion of a planet. So, for example, when we're talking about the first inequality of Mars, it'd say it has a year of 686.5 days. That's part of its first inequality. You would say that, and I'm making up these things because I forget where the line of Absides is, but you'd say that Mars generally moves fastest in Cancer and slowest in Capricorn. So that's overall, if you looked at it over 100 years, Mars's speed against the stars changes, both because of what it's doing and then thinking ahead to Copernicus, the fact that we on the Earth are moving around and looking at it. In Copernican terms, the first inequality is Mars moving, and the second inequality is the Earth moving. For Ptolemy, the first inequality is Mars moving with that equant, so its speed changes. And the second inequality for Ptolemy is the epicycle. That's what makes it move backwards every so often. For Ptolemy, the epicycle has the exact same timing as the sun around the Earth. For Jupiter, the epicycle has the exact same timing as the sun around the Earth. For Saturn, Ptolemy's epicycle has the same timing as the sun around the Earth. Can you guess for Venus?
Yeah.
The inner planets is different. The deferent has the exact same orbital time as the sun around the Earth. So, if anyone looking at Ptolemy's system, it's very obvious every planet moves in a way that's connected to the Earth and the sun. So it's not exactly hidden. There's a good video on that in part 1 on the new website, but the video doesn't seem to be working over this. So, but you'll be watching that on your own before next week. So that'll be good. Anything else there on part one? Just the main points to reiterate them. This is what comes out of it, is some basics of some of the terminology, the fact that the different hypotheses are equivalent, that there's no real difference between them because they're all using the mean sun. And that if you use the actual sun, the difference in Mars's observational position could be 2 degrees different, which is definitely big enough to observe. So those are the main points. Those are the main specific points. The other big physical point Kepler makes is that if the planets aren't held by, ethereal spheres, which he does not believe there's any ethereal spheres moving the planets, that there's also got to be some cause of their motion. And he's already wondering, how is a planet going to move in a circle anyway? Like, how is it going to know? Okay, the planet's not moving around the sun, it's moving around a point near the sun. How does it remember where that point is to always be the right distance from it? Once you start thinking about physical causes, everything becomes a problem. Moving in a circle is really hard. Okay, any other questions about part one?
You said the locations of the retrogrades bunch up from Mars.
Yes.
How long was that known? Just for a long time?
Sure.
Oh yeah.
Yeah.
It's noticeable enough that they notice that.
Mm-hmm. Mm-hmm. I mean, if you told me, hey, you know what? We did this thing. We've been observing for 1,000 years since you, and look, they're all bunched up here and here. You'd say, yeah. That's because of the equine. It moves faster over there, so it's less often there, so it doesn't have as many retrogrades there, just because it's not there as much. Mm. And because it's moving so fast, the epicycle can't pull it back. It's harder for the epicycle to pull it backwards. So when it does go retrograde there, it has a much smaller retrograde loop. When Mars is on the other side of the sky, where it's where it's closer to the equant and it moves slow, the retrograde loops are bigger because the epicycle is more able to dominate and pull it farther back as it passes it in front of the Earth.
Yes, these animations are really exaggerated. Actually,
no. That Mars one's not at all exaggerated. Oh yeah, sorry, yeah. The blue one with the gumdroppy looking thing is, but the new ones on the new website where you saw it moving against the sky and you saw them all, those are not exaggerated.
Oh really?
It really bunches up that much. Oh, what was the latitudes are exaggerated, which I regret having done, but it's just to show that there is some latitude. It's so small you can't see it unless it's exaggerated, but it is exaggerated. But the longitudes, those are real. It really makes that much of a difference.
Wow.
I think. They seem awfully large now that I'm... Okay, maybe they're exaggerated. I can't remember now. All right. Okay, any other questions, or can we look at part two? Okay, on to part two. And you can also jump in the middle with questions. That would really be fine, because this is tough to go over without knowing what your audience is and isn't getting, because it's all really complicated, and it's hard to know where people are without finding out where people are. So, okay, let's switch over to this this view here. So, in part two of the new astronomy, Kepler is going to create a model of the first inequality. And the first inequality is?
The motion of Mars.
The motion of Mars itself for Copernicus and Kepler. And Ptolemy would call the first inequality
motion of the epicycle?
the motion without the epicycle.
Yeah.
The point that the epicycle is spinning around a point that speeds up and slows down, that's the first inequality. And then the epicycle is the second inequality for Ptolemy. So in part two, Kepler's going to look at the first inequality. He's going to look at the motion of Mars for Copernicus, Mars around the sun, which is moving for Tycho Brahe, or the motion on the deferent with an equant if you're Ptolemy. And I had showed this picture before, but this is how he starts building up his way of doing it. These observations made when the sun, Earth, and Mars are lined up, these eliminate the second inequality. These observations are called being made at opposition, because the sun and Mars are opposite the Earth. They're also called acronical. That means rising at night. In other words, right when the sun is setting, Mars is rising. You know, Mars might rise at midnight. You might never see Mars many nights of the year because it's too close to the sun. You can't see it during the daytime. So when Mars rises right when the sun is setting, that's this sort of lineup, acronical. Those are words you might see for it.
And it's the real opposition, not a mean sun opposition.
Right. I'm not even going to talk about the mean sun anymore. It's very important, and the videos at the end of part 1 do a good job of getting it across, but the videos don't play over YouTube, so you're kind of missing something on the mean and apparent suns here, guys. Sorry. So Kepler is going to build up a model using this. Here, let me show you how he's going to do it. So he's going to build up this thing. He calls it his vicarious hypothesis. What does vicarious mean?
You're experiencing something via something else.
Experiencing something via something else. Yeah. Right. It's not direct. You experience something vicariously. You didn't really experience it yourself. You sort of heard about it from someone else by proxy. What Kepler's making in his vicarious hypothesis is a hypothesis by proxy. He's going to make a way of explaining how Mars moves, and he doesn't really think it's the way Mars really moves, but it's going to stand in for it. Mars is going to live vicariously through this hypothesis. It's going to have a wild time. So,
taking the place of another person or thing.
Taking the place of another. There we go. Substitute. I think it gets. I think in the Spanish translation of the book, they call it the substitute hypothesis. So we got these two assumptions, and you see on your screen here. So now there's two anomalies. Anomaly means something weird. In astronomy, it just means where something is. It actually means something very common. So there's an apparent anomaly where the sun sees Mars. Apparent means like you used your eyes and some apparatus and went out at night and looked at something. The mean anomaly is where the equant point around which Mars moves always at a constant speed would have seen the planet. So these are the ones that are actually used by Kepler. They're a little bit different. You can look at them. Can you see the difference? They're not exactly the same shape. For the four oppositions of Mars that Kepler's using, on the right in the red, that is where Mars was that night. That's where the sun saw it. On the left, the relative angles between the directions, that tells you how long it was in between those observations. So for example, let's take a look at the top two. Is the angle between the top two blue spots bigger or smaller than the angle between the top two on the red ones? The blue one is bigger. So is Mars moving faster or slower than usual in that direction?
Faster.
They're both slower and faster.
Is this time it takes to traverse that angle?
What is?
The blue one?
Yeah, the blue is the time to traverse the angle, right. So on the left is the times. Yes.
Oh, just faster.
Yeah, it moves slower in this part because it moved. If you look at the angle between the red spots, it's however many degrees that is, like let's say 110 or something. The angle between these blue lines here, it looks more like 120. So the time on the left was longer than the amount in the sky that Mars actually moved between those two times. So it's going slower in that direction. That's a hint that the equant is more in that direction, roughly speaking. Let's look at how this all gets put together. So here you've got, okay, so here's this animation. Okay. Now, when Kepler did this, it was way harder for him than anybody else. This is how, oops, that settles down there. Okay, so here you've got the way that Copernicus would have solved this. Copernicus used 3 observations, 3 opposition observations. There we go. Copernicus used 3 opposition observations. And he was able to do some math and say, well, if the times between the 3 observations were this, this, and this, and the angles between the observations as seen by us are this, this, and that, then the only way that you could have it be moving in a circle and have all these angles satisfied and have the center of the circle be directly between the equant and the sun is this. Let me just say that one more time. So Copernicus made an assumption following Ptolemy. Actually, Copernicus didn't really use an equant, but that's in chapter 4, and we're not going to talk about that right now. The assumption was that between the sun, well, the mean sun, tough to talk about. For Copernicus, between the sun and the equant of Mars, the point around which it appears to move at a constant speed, which is also a totally weird idea, that the center must lie directly between them. That's an assumption Copernicus made. It's not an assumption that Kepler makes. So when he's doing this problem, he can't just use 3 points. Because if you've got 3 points, there's a lot of ways you can orient these things so that the center lies somewhere between the sun and the equant. Look, there's another way it could have been. It could have been up here. It could have been over here. There's a lot of possible answers. Kepler.
How do you choose the blue lines from the red lines?
I mean, where do they come from?
You have the red lines, they're what you observe.
Yes.
How do you decide what those blue lines are?
So the way the blue lines would be determined, if you got a copy of your book, now the question here was how do the blue lines get determined? If you got a copy of your book, go ahead and open up to, let's say, chapter 15. Okay, and at the end of chapter 15, there's a table where Kepler has the 12 observations that he's going to use to make his model. For each of those observations, he's got where was it longitudinally along the ecliptic line that passes through the 12 constellations of the zodiac. Where is it left to right, east to west? And where is it north to south? What's the latitude? In the table, he's got the longitude, he's got the latitude, and he's got when the observation was made. So he calculates the mean longitude, which is the blue line in that picture, just based on the date. So, you know, if the observation number 4 was made on March 6, 1587, and observation number 9 was on December 13th, 1597, he would just look at the number of days between those 2 observations, divide it by 686.6, which is the number of days in a Mars year, and whatever that angle is, that's the angle between those 2 mean longitudes. So the red lines are where you saw the planet. The blue lines are when you saw the planet. But if you've got the book on page 248, that table at the end of chapter 15, that's all you need. All he's got is the date, the longitude, the latitude, and then he calculates the mean longitude from that.
And he makes a circle between the 3 points.
Yes. Yeah. Now, Kepler does not assume that the center is directly in between the sun and the equant. So he has to use 4 points. And that's why the vicarious hypothesis is so hard for him to calculate and determine. You know, it takes him, I'm not going to do this. There we go. Okay. So after, 70 adjustments, he arrives at this. And he says, this is the best possible orbit. We've got a line of apsides. We've got a direction, a line along which the sun and the equant are. This tells us where Mars moves at its very slowest and where Mars moves at its very fastest. We've got the distances between the red sun in the black center, and the black center in the blue equant. And we've got the orientation of the blue lines. That's called the epoch. Because the reason I bring that up is that the blue lines, you can rotate the blue lines around. They don't have a specific direction in space. Only the angles between them are known. So to solve the model, you have to say, well, what is the exact right, it's called the epoch. So Kepler, after 70 trials, there's a nice picture of it. He makes this beautiful vicarious hypothesis. And there it is in all its glory. So this vicarious hypothesis was made using the assumptions of the ancients, as he calls them. I don't know if Tycho Brahe would have been offended at being called an ancient. He only died a few years before that. But so the assumptions are Mars moves in a circle, and there's an equant. And the center lies on the line connecting the sun and the equant. That's it. So we've got circular motion. What does Kusa think about circles? And we've got there's some spot that if it watched the planet, like it was a lighthouse rotating around that. In other words, if you had a circular atoll or however you say that, if you had a nice circular atoll and you had a lighthouse off center and that was the equant, its beam along the beach of the circular land area, that would be the motion of the planet. Another way you can think of the equant. So those are the assumptions. Kepler made this vicarious hypothesis. He tests it out by comparing where it predicts Mars will be with where he observed it. And he uses all 12 oppositions, all 12 observations that he has. I'll show you the differences, show you what he finds here.
Was the blue dot the equant?
Yes, the blue dot was the equant.
Okay.
Here, let me take a look back at that again. Yes, here we got the blue dot is the equant.
The dark blue dot.
Yeah, the blue. It's hard to see. The three dots around the middle of the picture here are red, green, and blue. Red's the sun, green's the center of the green orbit, and blue is the equant around which the mean longitudes, the mean anomalies, and those angles measure when Mars was seen. The angles around the red are where Mars was seen by looking at it on those special days when the sun, Earth, and Mars lined up, so we know where the sun would have seen Mars.
And you said something about Copernicus insisting that the distance between the equant and the sun had to be exactly bisected?
Copernicus said that Copernicus actually didn't use an equant, he used 2 epicycles, but it's equivalent to him saying that the distance between, that the center of the orbit is going to be right between the sun, the mean sun, it's going to be right between the sun and the equant. That it has to be right in the middle. It's got to be bisected.
That one's not, though.
The vicarious hypothesis is not bisected. Ptolemy always bisected. Tycho did not always bisect. And Copernicus had the freedom to not bisect. But he held the, now that I'm saying that, it's hard to remember everything about that big book.
Anyway, you can keep going.
Why does Ptolemy assume that?
Yeah. Seems odd that it would be.
I think that, well, just using a circle doesn't work. Just using an eccentric is better. Adding an equant makes it even better. If you then adjust, should it not be bisected, you could make it even better, but Ptolemy was done making it better. I think that's why he just stuck with what it was. Plus, all the work you have to do, if it's not going to be bisected, it's a real pain, because there's no formula to do it. If you assume it's bisected, you don't have to do any trial and error like Kepler did for a year. You just, it's just, if you look in the Syntaxis or the Almagest, or if you look in Copernicus's book, it's in that, the great book that includes those. You can see it's a few pages and they calculate everything. They don't spend, they don't write out a book worth of calculations doing all this hard stuff like Kepler had to do, because they can just calculate immediately where is it. So I think those are the reasons. He didn't have to, would have been hard, and he just didn't. Even if he wanted to, but his observations weren't good enough to make it worthwhile anyway.
So if all you want to do is forecast wars and births and deaths of kings, it's good enough.
Yeah. So Kepler's was great. These are, you can see on the screen here. This is how far off it was for the different years that the observations were made from. Those last two, 1602 and 1604, Kepler made those observations himself. Tycho was dead. So the first 10 came from Tycho Brahe. The other thing is that actually none of these observations directly came from Tycho Brahe, because since Tycho Brahe was using this mean sun and figured that Mars moved around the mean sun, not the actual sun, Tycho didn't make any effort whatsoever to observe Mars on those days when the sun, the Earth, and Mars were lined up. He would make a big effort to make sure that when the fake sun, Earth, and Mars were lined up, he measured it. But the other days, he didn't really care that much. Fortunately, he measured a lot of things all the time, which is great, because if he only measured what he was particularly interested in, Kepler would have been, he just couldn't have done a lot of the things that he did in the rest of this book. Anyway, let's keep going. So, anyway, you can see those numbers are very small. Kepler considered Tycho's data to be good within a minute or two. A minute being a 60th of a degree. Wow, no telescope, and he did this. Some guy at this Kepler conference I went to in a few years ago, he had actually taken Tycho Brahe's observation books, put them all on a computer, and then used a program to compare them to what Tycho should have observed, and he really is within a minute or two. Like Tycho, he really was that good. So yeah, and it's great. If he wasn't that precise, Kepler couldn't have done what he did. Okay, so here you see these numbers. They're all like 2 minutes or less. Fantastic. Kepler's vicarious hypothesis is the best thing that's ever happened. It's more precise, more accurate than anything anybody's ever done. It's actually equally accurate as what Longomontanus claimed he did. But now here's the thing. There's in that vicarious hypothesis. Let's look at this picture of the vicarious hypothesis again, because there's several things assumed in it. What are the parameters of this model again? Do people name? What are the things you have to? What are the things that you say here? I know this, this, and that, and that's all I need to know Mars's orbit. What are the parameters?
Where you observed it and when you observed it.
That's what goes into making it. When you've got your answer, what do you have to specify to say here's the orbit?
Line of apsides.
You got to know the line of apsides, right?
Longitude
Which longitude?
of all the observations.
Well, yeah, we got the data that comes into it, and then when we're done, now, like the vicarious hypothesis itself, to characterize it, you'd say Kepler's vicarious hypothesis puts the line of apsides at 10 degrees Leo.
The distance
I made it
between the where you bisect.
Right, the distance between those 3 points. Those are called the eccentricities. So there's two eccentricities: the eccentricity of the eccentric between the red and the green points, and the eccentricity of the equant between the green and the blue points. The line of apsides, two eccentricities. Anything else?
Quadrilateral.
Look at the size of the orbit.
There's the size of the orbit. That doesn't come up with this, though. There's no size of the orbit for this vicarious hypothesis, because we're not comparing it to anything. We're just looking at Mars moving. The last one was the epoch, right? How do you align the blue? Where's 12 o'clock on the equant's clock, in other words? So those
the line of apsides?
No. I mean, you can make it that after. Okay, well, but then you say, well, what time were all the previous? Not exactly. I mean, yes. Once you know it, then you. Yeah.
It's like you knew.
It's all right.
How many hours between each? You didn't know what numbers they were pointing at.
Yeah. Right.
Oh,
Exactly.
Yeah.
Yeah, you knew. Yeah, the relative.
You knew it was between 4 numbers apart. You didn't know. It was between 2 and 6, or
Okay.
3 and 7.
So, right. So one of those things was those eccentricities. That means that we know something about based on the whole size of Mars's orbit, how far its center is from the sun. That comes from the eccentricity of the eccentric. What Kepler did was, and I got so sick of the Java updater that I removed Java, and now I can't show this animation. You can see that picture on the right. You know what? Just to describe it is fine. Instead of using the motion of Mars around this way, Kepler used the motion up and down, called the latitudes, to have a different approach to the planet, and he was able to calculate how far Mars was from the sun when it was close and when it was far. He was able to actually figure out what should the eccentricity be based on distances. In the vicarious hypothesis, you know, there's distances in the model, but they don't come up because you're only looking at the direction you see Mars. So Kepler, by using the Earth and Sun and Mars and latitudes, is able to figure out where Mars's center really is based on its distance from the Sun. And it is not the same as the vicarious hypothesis. In fact, you'll never guess where the latitudes say he should put the center of its orbit. It looks like it should go right in the middle. So he says, well, maybe Ptolemy was onto something, because it looks like from the latitudes that the eccentricity, that the center should be right between the sun and the equant, that the eccentricity should be bisected. So Kepler says, let's give this a shot.
So constructing those triangles, you're saying the latitude triangles.
Yeah.
Taking the distances and then the latitude would give you the height of the triangle. Constructing those triangles gave him the real center of the orbit.
Yeah, to show the picture here. Yeah, on the right, so he had to assume the Earth's distance from the sun, which he later doesn't quite agree with. He gives rough numbers because of the uncertainty here. But yeah, based on doing some simple trigonometry, A is the sun. He's able to calculate how far away from the sun D and E are. The aphelion, farthest from the sun, and perihelion, E, closest to the sun, of Mars. And then he can find out that spot K right in the middle. And so he can measure AK, the real eccentricity. And the real eccentricity fits about halfway in between, basically right halfway in between the sun and the equant. So Kepler says, all right, we'll bisect the equant. He kind of wanted to anyway. We'll get to that. He's got a funny quote about that. So let's take a look at this picture here. Hopefully this will show up for you. There's two models on your screen. On the left, in green, is the vicarious hypothesis. On the right, in orange, you see, and these are not exaggerated. These are real here. Wait a minute.
That's okay.
Okay. On the right in orange, you get the adjusted vicarious hypothesis, where he puts the center right in between the sun and the equant. He bisects it. That model doesn't work anymore. You can see up on the top there the differences that he calculates. So he gets about 8 minutes difference between the bisected version of the vicarious hypothesis and reality.
The left is the longitudes and the right is the latitudes.
On the left,
one based on the latitudes.
Adjusted to have the eccentricity based on the latitudes, right? Yeah, he kept the line of apsides and everything, but yeah.
What determines the point of the green dot, which is the vicarious hypothesis, instead of like the bisection?
It was just good question. The green dot was determined just by where to put it to make the model work the best, to explain where the longitudes would show up. When he took the 4 observations and tried to work them out so they make a circle, that was just the best spot that worked.
Basically, that picture. You should look at that picture. That's it.
Oh yeah. Okay.
So the other models that were used, they never took into account
So that's
latitude?
that's the green dot there.
Or the other models that were used, they never took latitude into account at all?
No. Latitude was insane before Kepler. It was absolutely crazy. Like it was just so crazy. So like Ptolemy, you would say that, okay, here's this, well, not the sun, Earth, so Mars' orbit's inclined, and then he'd say, well, now here's the epicycle. The epicycle's not inclined. The epicycle's in the same plane as the sun moving around the Earth, but then he would say that it would jiggle. So Copernicus had the same thing. Copernicus, he said, okay, this is inclined, but then Copernicus, they were so weird. They would say that the amount of inclination, how tilted the orbit was, it would wobble during the year. It just, yeah, before Kepler, everybody looked at longitude and latitude as really very separate problems.
But it would wobble like unpredictably, or was there a...
No, they had a it was just like they had a bunch of epicycles. I haven't looked into the latitude theories that much, but they weren't, Kepler's, there isn't any latitude theory. It's just, it moves, it is how it moves, and then there's your latitude. But all the other guys, it was nuts. So.
And part of this was Tycho Brahe's data. That's how you could do the latitude set.
Yeah, because that's how he does. He says, let me read this quote here. So after he finds this 8 minutes error, this quote's worth reading, even if it's in this font. This is a fall through. He says, you see that the very greatest error from the observations reaches 8 minutes. And this is in Mars, which has the greatest eccentricity. It is therefore less for the rest of the planets. Now, Ptolemy professed not to go below 10 minutes, or the 6th part of a degree, in his observation. But since divine benevolence has vouchsafed us Tycho Brahe, a most diligent observer, from whose observations the 8 minutes error in this Ptolemaic computation is shown. He calls it a Ptolemaic computation because he's using an equant and putting it and bisecting it. It is fitting that we with thankful mind both acknowledge and honor this benefit of God. For if I had thought I could ignore 8 minutes in longitude, then in bisecting the eccentricity, I would already have made enough of a correction to the vicarious hypothesis found in chapter 16. But now, because they could not have been ignored, these 8 minutes alone will have led the way to the reformation of all of astronomy and have constituted the material for a great part of the present work. So after Kepler made this fantastic vicarious hypothesis, he immediately breaks it by saying it shouldn't include anything that we know is wrong. This distance we know is wrong based on the latitude, so let's fix the distance, and now the longitudes don't work. So you get either one, you can't have them both. The longitudes are good, and the distances are wrong, or you fix the distances of the latitudes, and then the longitudes are wrong. So there's just no way to fix it. What this means is, he says, let me read this quote here, which he concludes with, that right, put it on the screen. That second brownish quote there, he says, the blame for this discrepancy among the different ways of finding the eccentricity, I'm repeating this over and over so it will be remembered, falls entirely upon the faulty assumptions studiously entertained by me and in common with Tycho and all who have ever devised hypotheses. For the necessary consequence of this inquiry is that there is no single fixed point on the planet's eccentric about which the planet always sweeps out equal angles in equal times. The equant cannot exist. So this is a huge, huge revolution Kepler's making. So he ends part 2 with a model that works well for saying where the planet would be seen by the sun, but he knows it isn't right. And he leaves with the conviction, and more importantly, the ability to force this conviction upon others, that the attempt to use math and these mathematical assumptions to explain the orbit of Mars can't work. He went through and we didn't go through all the details in terms of how much care Kepler went through in getting the observations from Tycho, correcting them. Tycho's assistants were screwing up the observations by like up to 9 minutes. When they took out the latitude, they would make these adjustments that were huge and wrong. So, so you had to Kepler to fix that and do it the right way. Spent 70 trials getting this vicarious hypothesis as good as could be. Part of that was picking which 4 observations would end up making the model that fit the other 12 as well as it could. I don't think he just picked those 4 years and went for it. I think he tried other years to see what worked the best. It was a lot of work, and after all that, it can't function. So those 2 assumptions, circles, equants, can't work. That's a revolution right there. So this lets Kepler, he's now free to go into what he really believes. He's got this tool, the vicarious hypothesis is a good tool, and he's able to grab his readers by the ear and pull them along and force them to listen to what he's got to say. Because as Megan had brought up with these astronomers that Kepler was talking to, they didn't want to get it. They would not believe in anything physical. Forget it. She had mentioned this guy David Fabricius that Kepler kept in the most contact with. Anyway, at the end of the book, after Kepler he figured it all out, he's got the ellipses, it's all over, he writes David Fabricius a letter, he says, I've got it. Oh, they move in ellipses like this, and here's everything. And David Fabricius writes back, he says, good job, Kepler. I checked this out against observations. This ellipse thing, it's perfect. It gives exactly, that's great. But there's some way to do it with circles, don't you? And Kepler didn't write him back anymore. That was the last straw. He had enough of them. So that's the end of part 2. We're now going to move to part 3, where he reconsiders the Earth's orbit. But first, are there any questions about part 2? We'll look on the email here also, just in case, and check the YouTube comments.
I have a bigger question.
Mm-hmm.
Why, after having just gone through the vicarious, making such a big deal about this, like a year ago?
Oh, this one making the big deal about the vicarious hypothesis? Well, he's talking about metaphor and how you get things across that can't be gotten across literally, and how you force the mind to answer problems in a way that goes beyond any current thinking would allow you to. So if you think about what Kuza does by saying, the coincidence of opposites, right? Things that oppose each other in the rational world can actually, you find that they have a common origin in the intellectual world, and so on, higher up to God. So that things that, when you're looking at things from too low a level, the pieces can't fit together and they seem contradictory and impossible. That's your indication that you have to make a hypothesis and create a new concept in your mind. So what Kepler's doing with the people he's talking to, it's like what Socrates does in his dialogues. He's like, oh, you think A, do you? Oh, yeah. You think B, don't you? Oh, yeah. And well, B leads to C, right? Yes, Socrates. And C leads to D? Indubitably. And D leads to E. Nothing truer could be said. And E leads to F, right? That's right. And F leads to A isn't true. They say, oh, but I thought A was true. Uh-oh. And they realize that you put together their thoughts, they are opposite. So they have to figure out what is wrong with their overall thinking. So that's the importance of this. Kepler's not saying that this isn't, this isn't like the adjustment of a mean to apparent sum. I mean, that's a huge adjustment. Or, it's not like, you know what, Copernicus's eccentricities were wrong. You have to adjust them a little bit. Because I'm sorry, I said earlier the hypotheses were equivalent. That's not actually true. I mean, Ptolemy's model didn't predict Mars was going to be where Tycho said it would. Tycho was much better because he did more work and he had better data, and it was actually closer. But you could update Ptolemy with all of Tycho's knowledge, and then Tycho's wouldn't be any better than Ptolemy's. So this isn't an adjustment of a parameter. Like what Tycho had done could all be applied to Ptolemy without changing the actual approach to astronomy. It wasn't a change in metaphor, wasn't a change in thought. So I think Lynn's emphasis on it was that it shows that, one thing, math doesn't work, because that's what people were basing things on, was math. And Cousin had said, no circles, better, you know, what circle is so circular it couldn't be? What 2 points, you know, on an orbit, you might say, what 2 points on the orbit of a planet are so equally distant to the center that they couldn't have been more closely equal?
Mm-hmm.
What motion could be so equal to itself from moment to moment in terms of a distance or an angle that it couldn't have been more equal? You know, so, you know, these things, Cousin already knew it. You know, he says in the Doc de Ignorantia, you know, you can't have a circle or an equant. But what are you going to do instead? And that's that thing of opening a door, and then there's this huge cavernous cave in front of you that's pitch black, and you've got no idea what you're walking into. Put yourselves in Kepler's shoes to think that. You'd say, oh yeah, it's physical. Okay, where do you go with that? Where does that leave you? Nowhere at first. You got nothing to work with. Kepler still has no tools yet. So what he's done, and he's got his audience with him, is for them to say, Kepler's onto something. Guess we can't just keep fiddling around with epicycles and equants anymore, and you know, crystal spheres. And Tycho's calculations about the comet of 1577, Tycho showed it would have like blasted through a whole bunch of the spheres, so that kind of did away with the spheres too. So, but then you see, well, how is anything going to make it happen? So that's where we're going to head off to now in part 3. If there's more questions on part 2, let's have them. Okay. All right, on to part 3. So, okay, so part 3, it seems a little bit funny at first, because what Kepler does in part 3 is show that the Earth has an equant. This is after he just spent part 2 showing that an equant can't exist. But now here he is. So part 3 is on the second inequality, and in case you forgot what that means, he gives you a hint in the title of part 3. It says, Part 3, Investigation of the Second Inequality, that is, the motions of the Sun or Earth, or the key to a deeper astronomy, wherein there is much on the physical causes of the motions. Physical. Whoa. This part we can go through kind of quick, I think. Basically, Kepler finds that the Earth has an equant. And I don't want to go through any of the detail about how he did that tonight. Well, I'll show you one thing that's actually pretty awesome. Let me find this good picture here. Yeah, this is an example of thank God for Tycho Brahe. Thank God the divine benevolence has vouchsafed us Tycho Brahe, because this would have been impossible. Actually, it wouldn't have been impossible. This would have taken 7 years. Kepler does this wonderful technique of using a stroboscopic view of the Earth. Every 687 days, Mars is in the same place. Even if we don't know exactly where that place is, it's in the same place. What Kepler first does is he uses Tycho Brahe's vicarious hypothesis, because it's not vicarious. He uses what Longomontanus had worked out. And he assumes that spot in the middle there next to the Sun is the mean Sun. He says, let's assume Kepler's right about where the mean Sun would see Mars. So he knows where the mean Sun sees Mars, he knows where the Earth sees Mars, and he puts all these triangles together, and he's able to figure out what is the center of the circle that the Earth moves around. And it's not the mean Sun. He finds out that what people thought was the mean Sun was actually the Earth's equant. Well, what Copernicus would have called the mean Sun was actually the Earth's equant, not the Earth's center. So it's a very small difference. Here's the thing: is it's really hard to measure where the Sun is, Because unlike Mars, which you can see against stars, it's really hard to see what stars the sun is in front of, because the sun's very bright, and it makes it very hard to see stars that are anywhere even close to it. So there had always been a fair amount of uncertainty about the Earth's sun, the second inequality overall. Tough to tell. The length of the seasons, that works pretty well. With the right kind of equipment, you could figure out what time of day the solstice actually was. I mean, the equinox actually was. So by greater precision on the timing of the seasons, that would help you. But people knew it was kind of imprecise. And the eccentricity is very small. So Kepler's change is small. He says this won't really make any difference where you think you're going to see the sun. But by doing this very clever thing of keeping Mars still and watching the Earth from both the sun and Mars, when you have like two eyes, so you get the actual 3D vision, you get distances, he figured it out. So that's the first half of part 3. Earth has an equant. Now he gets to have his real fun, because already in the Mysterium Cosmographicum, he has a short thing about why is there an equant and why is it bisected. So mesmerizing.
Mm-hmm.
Kepler said, look, when you've got an equant, it makes the planet move fastest when it's far from the equant. And imagine if you're like rotating a light, you got this lighthouse, right? You know, if you got a boat that's really close to the lighthouse, you know, the light goes across the boat, you know, moves at a certain speed. If you've got a boat that's right, you know, or like some land that's very far from the lighthouse, the light beam is going to move much quicker against that land. So it's like it's moving along a larger circle at the same angular speed. So Kepler said the equant's not making anything move. It's just a clever way geometrically of letting the sun move the planets. So the sun makes planets move. When they're close to the sun, they move faster, because the sun's moving them. When they're far from the sun, they move slower, because the sun's moving them. And the equant just sort of makes that happen pretty well. So what Kepler shows in chapter 32 is he says, he makes it exact. He says, here's his hypothesis. The speed of a planet is inverse to its distance from the sun. So there's a physical hypothesis. Right. Not an equant. It's not a geometric motion that's always the same. It's a physical principle that's always the same. It doesn't describe a motion exactly. It says how the planets will, you know, how it will be moved based on where it is. Now we got to figure out where it is. You still have to put together an orbit that changes its distance to make it speed up and slow down. Whew. So that's midway through part 3.
And it's saying that the planets work in physical laws that are comprehensible to us rather than a mysterious domain unaccessible to man.
Right. And he gives a physical hypothesis really quick, and immediately following chapter 33. This is where Kepler compares this power from the sun to a magnet, to light, all sorts of. He gets into what his physical hypotheses are. You know, we wouldn't agree with all of his physical hypotheses today about specifically how the sun, you know, is the cause of the planet's motion. But he's got a physical hypothesis. He puts it together. He says in a later chapter there might be things about astronomy that we just don't know about. He said, for example, if we didn't know about magnetism, he wouldn't have been able to make his hypotheses. So, you know, he's saying that the more we learn about physics here, the more we can learn about the heavens. That's completely opposed to Aristotle, who said that the heavens are made out of some, you know, thing that's not material at all. And here is Kepler saying we can learn from what we do here and apply it out there. So we can have the same physics here, you know, and it applies up there. Now, in trying to apply it, let me just show one more picture from part 3. Yeah. So, here we go. The distance of a, that's a clear one, right? The distance of a planet from the sun tells how far it will take to move a certain amount. So on the left, you get a semicircle. so let's say half the planet's orbit, and for it to move each of those, 10-degree chunks, or however long that is, the time it takes will be measured by its distance from the sun. On the right, all those distances are put together in a flat way. Adding up all those distances is very close to getting the area of that semicircle. It's not exactly the same. And Kepler does not ever, in this book, believe that area time is a principle. It's not Kepler's first law. He doesn't even agree with it. Okay? He does conclude with it, we'll see. But Kepler doesn't believe that's a real thing. He says that he's getting the hunch that area could be a good way of measuring the sum of the distances. Just again, why would you want to add up those distances? It's because the distance from the sun tells you how long it will take to move a certain distance along your orbit. So, like every degree along your orbit, say how far am I from the sun? That's how many hours it'll take me to move 1 degree. Now I'm at my next degree. How far am I from the sun now? I'm a little bit closer. It'll take that many hours to move another degree along my orbit, so on and so on. So that's just to give the very short version of it. That's part 3. So he concludes. He ends it with his physical principle and with trying to implement some of the difficulties of doing it. Because the area isn't the sum of the distances, he doesn't really buy area measuring the time, though. Okay. Now, part 4.
You want to say something on why he doesn't buy that? I think there's some people would think that that's important.
Oh, just because you hear area time and all that, but yeah. Oh, are there any other questions about part 3? Okay, still alive? All right. Okay. Here's part 4. Part 4, here we go, here's the title of part 4. He says, investigation of the true measure of the first inequality from physical causes and the author's own ideas. So now we're going back to Mars. We took care of the Earth. That was important because if the Earth moved at a constant speed, unlike all the other planets, then there couldn't be a universal principle of motion. So that thing about finding that the Earth had an equant was really important because it removed the objection of, well, Kepler, that's a nice idea, but what about the Earth? It just moves at a constant speed. How do you explain that? Kepler says, no, it doesn't. It has an equant too, but it's really the sun moving the planets. So now in part 4, he's able to apply this to Mars. We're going to go back to Mars with what he's got from part 3 and the knowledge that he's not going to look for an equant and he's not going to look for a circle. As a matter of fact, he ends part 3 by showing how hard it would be to make a planet move in a circle. It's really hard. What physical cause is going to keep pushing the planet in and out so that it goes in a circle around a point that nothing is at? That's a hard problem. So he's, it does not move in a circle. Part 4, he opens up, he shows using some specific observations that Mars does not move in a circle. So he's,
You got that quote by Lim right there, equal areas, equal times.
Yes.
Can you say something again about why you're saying that that's not such a big deal?
No, it is a big deal. The only reason I brought it up for some reasons I didn't. It's one thing that awful British woman thinks that the distance law doesn't exist, and that's not
awful British woman.
That I don't even want to say her name.
The woman from the Kepler conference who spoke like that.
Or something like that. That awful bitch woman. She said that Kepler jumped straight to area time and didn't believe in the distance law, and it was just so insane. And I didn't have a big reason to bring it up. I just bring it up. People hear that Kepler's first law is... Oh, no. I guess the
But
first
it
law
is
is the ellipse.
It is an important principle, that the fact that they do move in equal areas and equal times.
Yeah, we'll get to that at the end of part 4.
Okay.
But see, I was just saying maybe too far in advance that he doesn't believe it at the end of this book.
Oh, okay.
He believes that it happens and it works, but he has misgivings about it. I'll put it that way. He doesn't believe it's a principle. Okay, so now let's take a look at, we're going to look at this hypothesis that Kepler has. And, you know, you might laugh at him for saying this, but he shouldn't. Okay. So this is chapter 45, and this is where Kepler finally puts forward an idea of what non-circular path a planet could move in. So here you've got, you can tell it's changing its speed. The planet goes quick when it's at the bottom, goes slower when it's up at the top. The blue dotted circle is the blue hashed circle centered on the sun. So Kepler says, well, let's say there's some, you know, it moves around the sun on some circle, and then it has an epicycle on top of that. The speed of that epicycle is slow here. And then it has to move, whoosh, it moves faster down there. The rotation of the epicycle is faster at the bottom. Kepler says, what if we made that epicycle move at a constant speed? Let's see what would happen. It would move quicker than that at the top and slower than it at the bottom. Is that the most exaggerated view? Yeah. So it means something roughly like this. Kepler knows it pulls in at the sides. So his first hypothesis is, let's say that it has an epicycle that spins at a constant speed. Obviously, Kepler's not expecting this to work, since he doesn't believe there's epicycles, and you know, this kind of a funny construction. So he has to try this out. The thing is that, let's see which of these has the best pictures here.
Is this big open cave you spoke of?
This is trying to work, yeah, trying to figure out some way of getting around in this big open cave. You got to try something. So, you know, this is let me see which is a good one here to show. He has I'll just show this picture here. Here's the problem with it. You've got this epicycle that's moving at a constant speed. So that means that you've got some idea of how far the planet will be from the sun at different periods in time. But the other thing is, how quick is the whole thing moving around the sun? That depends on how close it is. So that, in other words, the two things interact with each other, right? When you get closer to the sun, you move around quicker, but then that changes your distance from the sun. So how do you deal with these two things that have feedback on each other, that interact with each other? And some of the most painful chapters in the book, except for chapter 6, which is, I think that you'll find out when you start going through part 1. Chapter 6 might be the toughest chapter in the book. That if, just to be brief about it, he does a lot of very, very, very difficult and time-consuming work. And he comes up, I'll show a picture of this. So he comes up with these different, they result in different kinds of shapes. Kepler didn't draw these shapes, but you know, knowing what he did, you can get the, we can look back at them and see what they look like, based on his different ways of trying to implement this hypothesis of his. So that other one looked like an egg. This looks more like a, whatever that is. He even tries an ellipse in chapter 47. Doesn't work. In other words, he's trying to implement this power of the sun, and then you know. Anyway, so then finally, what he does, here we go, chapter 51. He builds up. Oh, he's got such good. Let me see if I got the quote. It's a really great quote. Oh, here we go. While I am thus celebrating the triumph over the motion of Mars, and fetter him in the prison of tables and the leg irons of eccentric equations, considering him utterly defeated, it is announced in various places that the victory is futile, and war is breaking out again with full force. For while the enemy was in the house as a captive, and hence lightly esteemed, He burst all the chains of the equations and broke out of the prison of the tables. That is, no method administered geometrically under the direction of the opinion of Chapter 45 was able to emulate in numerical accuracy the vicarious hypothesis of Chapter 16, which has true equations derived from false causes. I send new reinforcements of physical reasoning in a hurry to the scattered troops and old stragglers, and informed with all diligence, stick to the trail without delay in the direction whither the captive has fled. Mm-hmm. I shall begin by seeking out the distances of several places on the eccentric where the evidence was most trustworthy. So he starts to build up a some specific distances. And here you got them. So this is an aid to him. I think he calls this some of his spies that he sends out around the enemy's camp to reconnoiter and figure some things out. The direction this ends up going, though, jump ahead here. You know what? Okay, here we go. Here's this quote. Basically, he's got some hunch now of how far at the edges the orbit has to get pulled in, but he's tried and tried with this kind of silly idea of this constant epicycle, and it's just not working. So he didn't expect it to work, but he also doesn't know if it did him any good at all. And it was a lot of work he did trying to implement it. So he's thinking about it. You can imagine, maybe he's a little bit, imagine what you'd feel like if you were doing this. You open up the door, you're still trying to figure your way around, it's pitch black in there. But a little bit of light has been shed on the fact that he had used this constant epicycle. And so here's what he says in chapter 56. He says, "While I was anxiously turning this thought over in my mind, reflecting that absolutely nothing was accomplished by chapter 45, and consequently my triumph over Mars was futile, quite by chance, I hit upon the secant of the angle 5 degrees and 18 minutes, which is the measure of the greatest optical equation. And when I saw that this was 100,429, it was as if I was awakened from sleep to see a new light." Now, that number has to mean something to you already, or it's not just going to, automatically, jump up. Oh, 100,429, of course. That gives him,
well. Can you explain this?
Oh, what a secant is. Oh, yeah. Yes. So let me show you on this picture here. So 100,429. He had before. So let's take that number, 100,429. Double the difference. The 429, you double it, you get 858. That's exactly what Kepler had before for how much the ellipse should come in on the sides. He had figured out how that constantly rotating epicycle would have done whatever it would have done, and it was 858 was the width of how far it pulled in. And he knows that when he did that with that ellipse, he did an ellipse with equal area, equal time back in chapter 47, but it didn't work. It made it move too quickly in the middle longitudes and too slow at the apsides. So he's like, okay. And so now this 100,429 thing, 429 is half of 858, and he's looking for something that would be right between, or somewhere between his old ellipse and the circle. But he's not just going to, make an ellipse that's halfway in between. He would have to have some physical reason to try it first. So here, he does not have ellipses on the brain. Instead, what he does is he realizes that, so the secant would be the ratio between, say, BF and AF. Secant is the opposite of a cosine. You won't find the word cosine in Kepler's book. Cosines didn't exist. So cosine is a complementary sign, the sign of the complement. I think that's where the name comes from. Anyway, so the ratio of BF to AF is this 100,429. So here's what he's thinking. At the quadrants, at E or F, where it used to be pulled 858 inwards, if it could only be pulled 429 inward, that would be great. Well, BF is 429 shorter than AF. So he says, so he then applies it to another location, at V, for example. He says, let's take a line from where Mars would be on the circle and draw it through the center, and then drop the perpendicular AR to it. Then RV would be the right distance. At least it would be at the quadrant. So he says, let me try that everywhere on the orbit. So
RV in an ellipse is equal to BF.
RV, well, there's no ellipse yet. No, at the quadrant, RV is BF. Just at F, if you draw a line through B and then drop the perpendicular from A, it's just AB. So the length would be BF. So at this other spot, you would take that length RV and then apply it from A to find some spot there labeled correct distance. It's not actually in exactly the right place, but in other words, A to Mars is the same distance as R to V. And Kepler says, that will give me, I think that'll give me the right distances. This is what it ends up looking like. It ends up making this, he knows it's not symmetrical, the orbit that it produces. But that's okay, it doesn't have to be symmetrical. This is where he's at this point. Here's the thing. This is just some kind of hokey geometric construction. Like draw this line, drop it through here, get that length, and then apply it to something. Even if it worked, Kepler's not going to go with that. That's not physical. So he then goes through Mega Chapter 57, which, in broad strokes, Kepler introduces a magnet in the planets. So he says that their speed is based on their distance from the sun, and additionally, it's called the reciprocal motion, reciprocation, like a reciprocal saw going in and out. The planets get pulled towards the sun and away from the sun based on a magnet that they have in themselves. And so for half the orbit, they're pushing themselves away, and then they get up here and they start coming closer again, and that would make the distances come in and out. Here's the thing, is that he actually has to, he then goes through the actual physics of, man, very complex. I'll show you a picture of it. Just one picture, short version here. Based on the angles that the magnet is at, based on the angle that the magnet's at and how much it would like to maintain its direction versus twist and point towards the sun, he's able to figure out how much force that would then push on the planet towards or away from the sun. And he does the first integral where he adds up, is it sine? I forget now. Oh yeah, he adds up sines to get a cosine. So he actually does it, he adds them all up, and he sees that it does it. You realize the integral of the sine is the cosine. So he's got something like where the infinitesimal force on the magnet pushing the momentary force pushing the planet in or out, he adds it up, and it results in that distance that he had constructed in Chapter 56 without any actual explanation. And now he says, oh, this is why. It's because of the way magnets work. He's got a whole physical cause for it. He goes through all the physics, and then he says, sounds good. And then he, with the one slight adjustment to the construction he had before, which at this hour I'm not going to describe, he gets an ellipse. This ellipse works perfectly. The distances it gives are just right. They're what he calculated earlier. The longitudes with the ellipse are just right. They match the vicarious hypothesis. When he's testing it, he doesn't really use observations most of the time. He uses the vicarious hypothesis as his comparison. So at this point, he's done. He's figured out Mars. He's got that it moves in an ellipse based on the motion around the sun being caused by how close it is to the sun, and based on this magnetic power in each planet causing it to come closer to the sun or be pushed away from it. That together ends up making it move in an ellipse. He did not try the shape of an ellipse and see that it worked. He never does that. In chapter 47, he did it, actually. He tried an ellipse in chapter 47, and it didn't work. And so even when he does this construction in chapter 58 and 59, it's only after looking at it, after looking at what the physics does, he says, oh, wow, that's an ellipse. So it was a surprise to him. He wasn't expecting it. He never tried it out. So at the end of this book now, he's got, at the end of part 4 now, he's got a physical hypothesis for the motions. He's got a way of implementing it. He's got the result of what it ends up doing. He's got a model that works, that totally works, and that, like I said, even his best friend David Fabricius said was crazy. So this is the the time he was in, and it gives you a sense of why he composed the book the way that he did, because nobody wanted to hear this. He was such a revolutionary. Other people weren't implementing this, the Cousin method of approaching things. They were being mathematicians. And so through the vicarious hypothesis, he's forced people out of mathematics, and then by taking them along this path with him, they can realize you can get the same sense of discovery that Kepler's reporting he had, of piecing the whole thing together and having a hypothesis that's 100% physical in the end. There's no just shape in it. And then part 5, I'm not going to say anything about it, just that it's about latitudes. And I think he partly did it to be funny, because his method of latitudes is so easy. You just tilt the ellipse the right amount, and that's it. You don't have to add epicycles that change their sizes, which, or you don't have to make it wobble like Copernicus did. It's it. Here's its orbit. That's it. It's an ellipse that's been tilted. The last thing that he thinks about is that he believes that magnet that causes it to come in and out and makes the ellipse shape, he thinks that also could be tied to the inclination, because the nodes here's your orbit, you tilt it like this, these are where my fingers meet, that's the node if I tilt it right along that axis. That didn't really have anything to do with the line of abscissities for any of the planets. But Kepler knew that when you measure inclination, it's with respect to the totally arbitrary Earth's orbit. Inclinations are measured with respect to the ecliptic. It's still geocentric. So his goal was to, by using ancient observations from 2,000 years before him, try to figure out how the Earth's orbit, how the ecliptic is moving. He knew how Mars's inclination changed. He knew how Mars's nodes were moving. He knew that it was progressing, and he thought that if it was connected to the same thing, the only way to figure that out would be to figure out how the Earth's nodes are moving as well. And there's just not enough ancient data that's good enough to try to figure that out. But that was the last thing that he was ending with, was trying to figure out, how is the sun actually spinning? That the basis of the ecliptic shouldn't be the Earth's motion around the sun, it should be what's the sun doing. And then he'd finally have completed the Copernican revolution, which Copernicus didn't do that much of compared to Kepler. And you'd really have a physical thing all based on the sun. And so this is the first modern physics. It's not math, all physics. He doesn't even want to leave latitudes safe from the. He doesn't even want to leave latitudes exempt from the domain of physics. He's going to get it all. So, any questions about 4 and 5? Thank you. Any questions about 4 and 5? And oh, here's a question. Tell us the story of the fake Kepler site. Who knew Kepler was so politically provocative? All right, let me compare it with this super shitty website here. If you go to keplersdiscovery.com, I'll show you this. I will confess that these silly arrows I put at the bottom of anyway. Okay, so here's this dumb site called Kepler's Discovery. Oh, it's so bad. Anyway, it's just a total copy of the site that we made, but they did such a shitty job that they made tons of errors and they never fixed them because actually the hand of God prevented them from being resolved. Like, oh God, it's so bad. I'll tell you a secret about this. Let me find an appropriate one to make fun of.
Errors, though, which nobody else would notice except you.
Yeah, probably. Okay, it's true. Errors probably no one else would notice. Like this animation is exactly. Let me show this one. This is. They have no shame. Of course, yeah, they do have no shame. So. No, that's not it either.
First inequality.
No, where is that damn thing?
Chapter 1.
Oh, here it is. Okay, yeah, there we go. Yeah. Okay, so here you get the brand X. I mean, it's just so similar. It's hard to imagine. The thing with all the animations on the fake Kepler's Discovery site, which was it was actually really shocking to see this thing. It's like, wow, who would have thought that somebody would go through all the trouble of faking our site?
But no one knows when was it made. Like when did this?
This came out like right after ours did. It came out like a few months later. The thing is, all these animations, because on our website, the animations they're actually accurate. Like they're either made with Mathematica or they're Flash animations or they're made with ActionScript, which, in other words, like it's not like made frame by frame. The computer is calculating where to put everything. All of the things on this fake website, they actually made as frame by frame cartoons. All of them. I looked at every single one of them, meaning that in none of these did they actually know what was happening enough to program the computer to do it. So it's just like tracing, with like transparent paper over something else.
Like
so
taking pictures of our website and then like
like hitting print screen repeatedly and then like drawing it in Flash and then putting all the frames together. That's what all these Swift files are. Like this looks like it's like if you watch this one carefully, you'll find that the this one, yeah, okay. It's a small difference, but it's a big one here. That blue dot doesn't actually stay on the dotted line because the blue dot and the dotted line have nothing to do with each other. They're just a dot and then a line, and someone's adjusting it frame by frame. So anyway, this is the subject of that movie, The Harvard Yard, that we made. That think about it. Why would somebody do this? Like, okay, there's like no Kepler there's not like a whole Kepler site on the internet. We produce one. The LaRouche Pack, produces this guide to Kepler, and then someone else decides they're going to do it, and they also it's really I can't remember any more about. I mean, the other thing is that the epistemology is just totally wrong about it. So there's some bullshit about cones. Oh, you can't see what I'm looking at anymore. Yeah, look at this. It's just horseshit about cones. This is what pisses me off. This is exactly the wrong thing. Oh, you can't see it. It's fucking this ellipse bullshit here. Here, listen to this nonsense. Kepler had discovered that the orbit of Mars could not be a circle, but rather some kind of oval shape. We discuss his geometric demonstration here. Wow. This is another exact copy. No, this, I'm going to show you that one too. This is an exact copy again. Anyway, after ruling out various possibilities using a triangulation procedure that employed the physically false but accurately predictive vicarious hypothesis to generate orbital elements, no, Kepler postulated the idea of an ellipse as the shape of the orbit. He then used the elliptical model to generate a table of planetary positions and tried to make it look as if he had arrived at these results by triangulation.
Oh, it's like totally wrong.
We might criticize him for this method, but why did Kepler get it right?
So it had nothing to do with those chapters you just actually went through.
In other words, what they're saying is that, like, part of this came from this paper yeah.
How come this legal actions? I mean, if it's such a clear plagiarism, how come they weren't sued?
Well, we contacted a lawyer about it. Just that it's kind of hard to. I mean, it seems really obvious, doesn't it? But
yeah, doesn't it seem? I mean, you're saying it's so obvious. The animations are the same. They're almost exact copies. And I mean, and it was the date on it is so close.
Yeah, no, of course.
How come they weren't sued?
You'll have to talk to Barbara about that one, okay? Anyway, here's his main thing. Like, maybe this is why I was so angry about the ellipse. This is exactly this bullshit about the ellipse that people say. Anyway, they quote Donahue saying that. Anyway.
He just said that he couldn't have done what he did with, Mars staying in the same place because it's too precise.
Anyway. So it's just not true. So here you get this site. It gets put together to try to make a point. Oh, what's the background? Who did it? When? Well, I don't really remember that guy's name. Well, I don't know if we should talk on YouTube about exactly who did that. But it was connected to Harvard, which is why we made the Harvard Yard. So, if you think, in other words, it's just like getting to see in our own time the kind of things that Sarpi did, or that Conti did, or where people try to take discoveries and then make them their own to make a different point with them. Like this, I mean, this one thing I read about the ellipse is just, they should have copied the text too. They copied the figures and they said such nonsense. Anyway.
Do they quote Kepler at all on this website?
So I wonder if it's the exact same quotes. I don't know. I didn't even think about that. Are there any quotes that came from actually reading the book that weren't just on the other website? I don't know. Oh, sorry. I promised that I would show that.
Maybe they just didn't have a copy of the book.
I think they might not have. That would be the thing. Let me show you one more blatant plagiarism here. Because I thought this was a cheesy animation. Okay, here we go. But they liked it. So depending on which 3 points you use, you get different circles for what Mars is. Oh, this is the end of it. Anyway, okay, there you go. Instead of the circle coming in from the side, it grows out of nowhere. It looks nice with their colors, I'll confess, but I think I know where they got that idea from.
Didn't they copy some errors that were a couple of the animations?
Oh yeah, yeah.
Moved the wrong way.
Yeah, one of them was on chapter 51 here. because okay, so this is first time. Okay. Oh. Maybe they took it. Anyway, are there any other questions about the book here?
How did you say the magnetic hypothesis made the ellipse necessary?
The magnetic hypothesis made a oh god, this one's also totally copied. Well, I guess they all are. Oh, you know what? They took down the one that I'm thinking of, where they no, a little dance, isn't that cute? Okay.
We've also got a whole section on the
same exact color scheme on this one. Okay, you get it. You get it. They still okay. They still all right.
This is very emotional for you.
Yeah. This is a big thing. So okay, what else? Let's see here.
Oh, we had a question from Rachel.
Yes.
That you might
Sorry.
have heard.
How the ellipse was made by the magnetic.
Right. So how's the ellipse made by the magnet? It's the magnet's power. Okay, I know I'm going to say the word sine and cosine and inverse sine wrong here, so they might have to be rearranged, but something like this: that the power of the magnet to push the planet back, push the planet towards or away from the sun, is based on the sine of the angle, the sine of its angle from the line of apsides. And Kepler figures out that if you've got something that acts according to the sine and it's constantly acting, when you put that together, you get the cosine, or 1 minus the something along those lines, or you put together the versed sine and you get the cosine or whatever. That's it. You add up the versed sines, which are anyway. He does an integral. You get these cosines. That ties in with that secant, which goes back to that construction he had made, where you go take a line from where it would have been on the circle, draw it through the center, drop the perpendicular from the sun, and take that length as being the right length to get it to be from the sun. And then, you know, the reason that he puts that onto the perpendicular drop to the line of apsides from the point on the circle, I don't know what his justification is for putting it right there, actually. I'm not sure. He did know that it, I think that one, he might have actually just noticed that it worked. And then,
That number.
right. But the fact that that made an ellipse was secondary. In other words, if you, it's just a thing of geometry. If you draw a circle and then, you know, bisect it with a line, and then take a point, you know, like we just start drawing things out here. Take any point on that circle, draw a line through the center, drop the perpendicular. You guys can't see that at all, but Rachel can. Drop that perpendicular. Take that distance. And then put it right here on a line, drop perpendicular to the line of apsides from the point on the circle. You get this spot right here. If you do that everywhere, it actually makes an ellipse. But as Kepler presents it, he didn't make an ellipse. He didn't do what this bullshit website said. He had the reason it would come in that far was based on the power of the magnet. And when it always comes in that far in this way, it makes an ellipse. So. Let's see here. Vera wrote in something. He said, "The way Kepler's discovery is being taught in school is so straightforward." Okay, class, here are Kepler's 3 laws. That's all you need to know. Why did Kepler bother writing the book the way he wrote it, especially the New Astronomy? If I remember right, the first version of his first book, Mysterium Cosmographicum, does have errors, but chose to keep it in the second version. It's true. And he had a 25-year anniversary edition of the, I'm sure you didn't call it that, but the Mysterium Cosmographicum came out in 1596, and in 1621 it was republished. And like Mendeleev's Principles of Chemistry, Kepler didn't change anything in it. He added footnotes, like a lot of them, but he didn't disagree with the approach that he had taken as a much younger thinker when he originally wrote the book. So as far as why Kepler wrote the New Astronomy the way that he did, I'd like to do another class on that at the end of this, whole New Astronomy project, because it's tough to get into it if you don't know it's tough to do it at the same time as the content of the book. I mean, we did some of it today, but once you actually get into it and read through parts of the book yourselves and just become more familiar with it, it'll be a lot easier to get into and to make sense of. With lots of like letters from the people he was writing to and how people responded to his thoughts and all that. So the way he wrote it was, this is a serious thing, is like it took forever. I mean, it's pretty amazing that the New Astronomy wasn't translated until the 80s. There was a book written in the early 1800s called A Short Account of the Discoveries of Kepler, which is kind of like a Cliff's Notes to the New Astronomy. It's actually surprised. Some chapters are translated almost in their entirety, some are left out altogether, but there really wasn't a whole New Astronomy in English until the 1980s. What was I going to say about that? Whoops. Yeah, it's getting late. I think we ought to wrap up pretty soon here. Why he wrote it the way that he did. You're right. So some of the first people who were just reading summaries of it or didn't really know what happened, they took everything Kepler did at face value, as though he just this slander was that Kepler bumbled his way into discoveries. He was just trying this and that, and he had no particular rhyme or reason for what he did, and then he wound up doing what he did. He didn't actually do the research in the order it's presented here. And Donahue's got footnotes about that as you're reading through it, where in part 3 he's clearly using things that came from later in the book, a non-circular orbit for the Earth, for example, because he was doing all these things at the same time. He didn't really just show the equivalence and then say, now I'm going to make a vicarious hypothesis, and then put that aside completely and look at the Earth, Sun, and area and distances, and then go on to looking at the orbit of Mars, and then look at latitudes. He wrote the book in a certain way to make a point. It's written like a great play or something like that. I mean, it's a real work of art, the actual composition of it. Yes, yeah. So it's not just a narration of everything that he did. It's to get a point across to astronomers of his time. And us. When he knew in the harmony of the world, he wasn't just writing it for people of his day, that's for sure. Let's see, let me read that quote. This would be a good quote to end on. At the beginning of Book 5 of the Harmony of the World, Kepler says, I'll put it up. Now 18 months after the first light, 3 months after the true day, but a very few days after the pure sun of that most wonderful study began to shine, nothing restrains me. It is my pleasure to taunt mortal men with the candid acknowledgement that I am stealing the golden vessels of the Egyptians to build a tabernacle to my God from them, far, far away from the boundaries of Egypt. If you forgive me, I shall rejoice. If you are enraged with me, I shall bear it. See, I cast the die and I write the book. Whether it is to be read by the people of the present or of the future makes no difference. Let it await its reader for 100 years, if God himself has stood ready for 6,000 years for one to study him. That is a bold thing to say. So, okay. All right, so we're gonna have these, this series, working through the book with the homeworks. You got to do those homeworks. Let me tell you, if you want to get this, and you don't, forget it. You can't just do it by watching things. You got to get your hands dirty with it. And then, then we'll have some wrap up towards the end and see where we move next. But I definitely would like to come back at the end and talk more about how the book was put together from the standpoint of who Kepler was corresponding with and who his audience was. So, any other last questions? Okay. Let me just look on the YouTube comments. Okay. Oh, okay. Looks like that's it. So, thanks for joining, and the course series continues Wednesday at 7 with part 1. See you later.